Hello and welcome to Target JEE from BYJU'S. We're going to analyze a chapter here from the point of view of the JEE Advanced and the main exam, what happened in the last few years. Then we're going to do a quick, rapid revision for you and then some solved questions, handpicked for you. Let's start with electrochemistry in this session. So in the JEE Advanced exam, quite a favorite topic. In 2018, there were two integer questions asked, both on the Nernst equation. In 2017, there's one integer and one MSQ, multiple correct answer type question that was tested. The integer type question was on limiting molar conductivity and the MSQ was on electrochemical cells. 2016, one MCQ asked on Nernst equation again. 2015, two integer type questions, one on Faraday's laws, the other on molar conductivity. 2014, one MSQ on the theory of salt bridge. So the chapter was thoroughly covered in the last few years and a lot of weightage given to it. And it kind of makes sense. It's like a combination of everything in physical chemistry that came before it. So personally, I think it's an easy chapter if you have done the whole of physical chemistry. It's like a marathon. It's very difficult to just do electrochemistry and not do the others, because it uses ideas from thermodynamics, gaseous state, equilibrium, and also basic stoichiometry. So you need to revise all of this. If you do that, then this is actually quite a straightforward chapter, but it requires a lot of practice because there's a lot of formulae involved, just like thermodynamics. From the JEE main exam, especially in 2019, every session had at least one question. And a lot of these questions were either on the Nernst equation or on the standard reduction potential. Other ideas tested as general, as you would expect, would be on Faraday's laws. Some ideas mixed with equilibrium, cell representation, the way you would represent a galvanic cell, and also on conductivity of ionic solutions. So let's get started with the rapid revision now. All right. So electrochemical cells, that's the first thing you'd want to look at when you're starting this chapter. The different types, right? You're changing chemical energy into electrical energy and vice versa. So you have electrolytic cells, you use electricity to break stuff down, or galvanic cells, reactions that produce electricity. They're all redox reactions, and galvanic cells are spontaneous reactions. Electrolytic cells are non-spontaneous reactions, which is why you require additional electricity to make them happen. You then go on and revise what is the idea of E0 reduction, the standard reduction potential, and you form the electrochemical series. Lithium there is highly negative, which means that it gives you the plus ion very easily. It doesn't like being reduced, prefers being oxidized, H2O. F is highly positive, which means that it likes forming the F- ion. This is a very, very important idea. And the next important idea here is that E0 reduction is negative of E0 oxidation. Sometimes the JEE Advanced exam has tested this. So be careful about the basic definitions, how to interconvert from reduction to oxidation easily. Usually we use just reduction potential values. The really, really important idea that you should be careful about is E0 is not additive. All right. What do I mean when I say that? Delta G is additive. From that whole idea of equilibrium. Delta G is delta G0 plus RTL NK. You need to know this. You get delta G is minus NFE, which is the single most important equation in this chapter. All right. I'll get to more ones later, but this is the basic, and from here you can derive everything else. And delta G0 obviously is going to be minus NF E0. Delta G is additive. E0 I'm saying is not additive because look, sometimes it so happens with that the number of electrons is the same in any cell. You manipulate delta G values accordingly, and you can then add it because the number of electrons is the same. So when I say E0 is not additive, that's what I mean. There are shortcuts that you can use, and sometimes E0s are additive, but that's only and only when the N value, number of electrons, is the same. So actually, behind the scenes, you're still adding G0 or delta G values. This is important. I spend some time on this. Be very careful about this. All right. When E0 is positive, the reaction is spontaneous. You can get that from the delta G equation. We got that delta G was minus NFE, right? That's why. All right. E0 cell is E0 cathode minus E0 anode. These are all reduction potential values, remember. If I make it oxidation, it will be the other way around. So be careful. Reduction is always at the cathode and oxidation is always at the anode. Red cat anox is something that teachers like to teach. Next thing you want to know is, look, don't mug this. It's better to do it from first principles, but if you're doing this just for an exam, you need to know this, that the signs on the electrolytic cell and galvanic cell, the signs of cathodes and anodes, are opposite. They're on your screen right now. Don't mug it. If you're not convinced with what's on the screen, go ahead, go back and try and derive it from the first principles. Cell representation is the next idea that you absolutely must revise. A lot of questions in the JEE main exam have been asked on just this idea. Anode is always on the left-hand side, cathode is always on the right-hand side. And those two things in the middle, that's the salt bridge. Look at what you have in front of you right now, the concentration cell idea. See the electrodes first, then you talk about the gas, and then you talk about the ion that it forms. In case of H, we've got all three states here because this is the most most difficult idea that you could come across. You have different electrodes, a gas, and then you have ions. Salt bridge and the same setup over here. So this one's the anode, this one's the cathode. You could form many concentration cells, but the cathode concentration always has to be higher than the anode concentration for the EMF to be positive. Yeah, that's a very, very important idea because of this expression of E cell you have over here. Okay, E naught cell is going to be 0 because it's at equilibrium and you have the same substance at both sides of the concentration cell. Okay. E naught cell is going to be 0 not because of equilibrium. E naught cell is 0 because of the same concentration. If you're at equilibrium, then E cell itself will be 0. So anyway, moving on. Nernst equation, that's really, really important too from this chapter. Delta G is equal to delta G naught plus RT ln K. Now here, from this you can derive that E is equal to E naught minus RT by NF ln Q. Now this itself is the Nernst equation. Generally at STP you get this value to be 0.059 by N. And at equilibrium delta G is 0 and E is 0. That's what I was saying earlier. Yeah. So E is equal to 0 at equilibrium because delta G is equal to 0. Remember, for the concentration cell, again and again, E naught is equal to 0. E is not 0. E you get from the expression that we just saw a little bit earlier. Faraday's laws are the next thing you'd want to revise of electrolysis. Two laws, but you can kind of combine them in a way. First law says that the weight deposited is proportional to the charge that you provide to it. Now, charge is what? Q is I into T, right? So you get W is equal to ZIT, where Z is some electrochemical equivalent. W1 by W2 is E1 by E2. That's the second law. So you get that W is simply E into Q divided by 96500. That's Faraday's constant. This is something you need to know and very, very useful in solving JEE main questions. In the JEE Advanced exam, this is tested in an interesting way, not directly maybe, but this idea of, the first law where weight is proportional to charge, that is tested more, has been tested in the past. You never know what happens in the next exam, right? Conductance and conductivity. That's the next idea that you absolutely must revise. Although I think some students are kind of afraid of this, but it's really direct if you just do some basic 10th grade physics, yeah? I think 11th grade physics also, where you get that R is rho L by A, resistance idea. From there, just invert it, conductance is K by G star. There's a lot of new stuff, but G star is simply the cell constant and K, kappa, actually not K, kappa is conductivity, which is the inverse of resistivity. That's it. From here, you can derive many other expressions. Yeah, you have lambda M, lambda EQ, lambda M is molar conductivity, lambda EQ is equivalent conductivity. Basically, you take kappa per mole or per equivalent is you get that. There's a formula that a lot of textbooks give you. I think you just need to be careful about units because sometimes the JEE Advanced exam gives you different units. So you cannot always use that 1000 formula. All right. I think the best way to remember this part here is that lambda M, molar conductivity, is simply kappa per mole. Okay, so you figure out the units accordingly. We'll do some numerical and show you what I mean. All right. The limiting molar conductivity at infinite dilution is known as lambda infinity M or lambda naught M also. This is expression for strong electrolytes. There's a root over here. And for weak electrolytes, you have alpha equals lambda M by lambda naught M or lambda infinity M. So yeah, that pretty much sums up what we did in electrochemistry. There's some Kohlrausch law that also needs to be revised, and also cells. I know I didn't spend a lot of time on it because this is not tested in detail. The JEE Advanced exam usually doesn't make you mug stuff and repeat it, right? The JEE Main, on the other hand, sometimes, yeah, you need to know how some cell reactions work, especially lead acid, yeah? The equivalent weight of a lead acid battery has been tested in the past in the JEE Main and the Advanced exam, actually. But of late, there haven't been too many questions on you having to remember what a cell reaction is like. But hey, if you want to get a maximum score in this, it's a good idea to revise all the different types of cells that are in NCERT. Let's get started with some questions now. Okay, here's a question that can have more than one correct answer. An interesting one. What's given to us? We have the E naught values of half reactions, the overall reaction that you'd want to consider. There's the concentration of N2 plus given to us to be 0.1 molar and some A, right? MA plus, you don't know what that A value is. The voltage of the entire cell is 0.180 volts and the Q value is given to us to be 10 power minus 2 molar. That's interesting. So we need to look at the options. Yeah, the options say that Ma plus is some value, the concentration. The maximum work that can be done from this entire cell is this E naught cell and also A value. So what gives? We need to find A, Ma plus, whatever the concentration is, E naught cell and W max. There are the four options, that's what they are. So we need to find them out. Let's get started. Let's look at the approach first. What's the approach going to be like? Well, the first thing is we're going to have to do E naught cell equals E naught cathode minus E naught anode. That's a standard equation. Let's do that and we can get E naught. Once you have that, you know that from the Nernst equation, this expression over here, yeah, that E is equal to E naught minus RT by NF ln Q. We need to substitute that there. And in our case, because it's an STP, we can just use this expression directly where, you know, that entire value is 0.059 by N. A quick revision of what's what. So from here, we can get the N value and hence also figure out A. This figuring out of A, it's interesting. I'll walk you through it. Yeah, it's pretty interesting. From here, it's direct. I use the Q expression, you get MA plus. Q is just, you know, the product of the plus and the minus ions or whatever raised to the stoichiometric coefficients, right? Divided by whatever's on the LHS. So on top is LHS, on top is RHS, and on the bottom is LHS. Basically, the expression for K, the equilibrium constant. Yeah, very, very similar to that, but at any other point, not an equilibrium. If it was equilibrium, then E cell would be 0, right? And that's not the case. So we know it's not at equilibrium. Anyway, we need to find out the maximum work that can be derived from this, that we can do by using this expression work equals minus NFE. No work if it's at equilibrium 2. I keep saying that. I know it's maybe you already know this, but it's a really important idea. Yeah. Okay. Anyway, so look here. The given voltage is positive. Yeah, it's 0.180 volts, which means that E naught at the cathode must be greater than that of the anode. That's a very important idea. We'll use that to figure out what's to be done next. So here, hence we know which one's the anode, which one's the cathode. So this is going to be 0.4. Let me write the full thing now, right? 0.400, 0.240. I'm going to use these values in this manner because of this idea here. So E naught cell is simply going to be equal to 0.160 volts. Okay. The reason I did it this way is because as I said, the E naught value was, the voltage given was positive, and that would happen only if we choose the cathode and the anode in this manner. Okay. So that's really important here. This, if you mess the starting point up, the rest of the numerical will give you very, very weird answers. So yeah, after this, we just need to just substitute in the Nernst equation and get the value of N, right? So what's the Nernst equation here? It's been given to you, although the actual value is 0.059, and the question is I asked you to take 0.060. So let's use that, yeah, to our benefit. So here, from this Nernst equation, you have 0.180, which is basically E, right, is equal to E naught value is what we just calculated, 0.160. This is E naught minus 0.060 by N log Q, right? Q was what? I think Q was 10 power minus 2, right? That's what we had written down here in our givens. Yeah, Q is 10 power minus 2. So let's use that. Q is 10 power minus 2. All right. Here, log of 10 power minus 2. So yeah, this gives us a nice and neat value. You get this to be 0. What do you get? 2? Yeah. 0. This is, oh, not 0.2. This is 0.02. That's bad math for me. Is equal to negative of 0.060 into minus 2, right, by N. So yeah, this gives me N value to be 6. Yeah, that's it. I've just, this minus gets, this becomes plus, 2 into this becomes 12. So yeah, N is 6 here. So how am I going to get A from here? I told you there was an easy way to do that, right? Let's see. Check out this expression. I'll let this be on your screen. Yeah, N is equal to 6. Let's hear. So this expression is A plus is not N, right? We need to find out the A value here. So I've just written that as basically N is the same as A. Okay. So this is the expression that you would have here. And this is 0.4 volts. This is again the cathode. I'm just going to write that again. This is the anode, which is why. And I've reversed the sign here. And in terms of, because this is getting oxidized, right? So that's why the sign is opposite. This is still reduced. So don't get confused by all this. Get comfortable with it actually, switching from oxidation to reduction and how that affects the E naught value. Anyway, so what's the total E naught going to be here? We already found that out. This is going to be 0.160 volts, right? Now, this sort of a setup is possible, because total number of electrons is 6. This sort of setup is possible only and only if there are two possibilities. Yeah, I could have, since there is already 2 electrons fixed over here, the two possibilities are it's either 1 and 6 in the two separate things, in the two separate reactions, the number of electrons, or 2 and 3. Yeah, only these two combinations would give me a total n factor, or not n factor, the number of electrons to be 6. But here, since this is already fixed at 2 electrons, this has to be 3. Yeah, this n value has to be 3. Only then do you get 6 electrons. And what that would mean is you would multiply this entire equation with 2 and this entire equation with 3. That's what that means. The 6 and 1 thing doesn't work out because this is already fixed at 2. Yeah. So that's the overall reaction now. So you would say that n is 3, which is basically m3 plus 3 electrons, 6 electrons. I'm going to skip the electrons. So let's just remove that, and you have n, which is was a solid, and this is 2n, right? Let me what do I do here? This is 2. This is 3. This gives me how many do I have? I have 3 and 2 plus AQ, and how many m do I have? I have 2m plus 2m, which is solid. Let's see. So there's 6 plus 6 charge here plus 6 charge here, and the mass is balanced to 2. Mass to 2m and 3n. So yeah, this is the fully balanced reaction. Note that E naught does not change. Yeah, whatever I do with this, multiply with 2, 3 or whatever, E naught value is going to be the same. Yeah, that's what I meant by E naughts are not directly additive, but they happen to be additive if the n value is same. In this case, we got both of them to be 6. Yeah, this is the n value that's the same here. So this is why it was additive. Okay, moving on. So we've got that A value is equal to 3. Option said 2, right? I don't think that's correct then. I don't think that's correct. So A is definitely 3. Let's see what's next. Next idea was to use this Q factor, right? Q value. If Q is equal to 10 power minus 2, what does this say? We can get this concentration of Ma plus. Yeah, we need to do that now. Let's just write it as M3 plus now, since we know that. We need to know this concentration. How do we do that? Well, look at this expression on top. Let me scroll up again. Yeah, let's leave this equation here. For our reference. So this Q is simply going to be N2 plus whole cubed, right? Divided by M3 plus whole squared. Did I do that right? Yeah. N value is 0.1, right? So I get a 0.1 cubed divided by M3 plus squared. This is what 10 power minus 2 is going to be. And that's it. So I take this I take this to the other side. This becomes 10 power minus 5. Everyone's happy. Let's see. I get M. Oh, now this could stay here. Okay. M3 squared. Let me take this to that side and bring the other one here. Okay. Too many arrows. Get rid of them. And all of this. Hold on one moment. Here you go. Okay. Let's take this one this side and this one this side, because that's what we want to do. M3 plus square, right? M3 plus whole squared is going to be equal to 10, this is 10 power minus 3. This is 0.1 10 power 3, right? 0.1 power 3 into 10 squared. Okay, what gives? So looks like M3 plus is simply going to be equal to, yeah, this is going to be 10 power minus 1, right? Under root of that. Look at that. So this is what matches. Interesting. So we've got E naught to be something that's over here. Yeah, this is the E naught value. We've got this over here. What else was tested? A. All right. So we've figured out 3 of the options. Let's figure out the 4th one, which was this W equals NFE, right? The W max value. We need to figure it out. The maximum work that's possible. So let's see. So this would simply be equal to minus 6. We've figured that out. N was 6. F is F. Let's just keep that as this. E. What's E? E is 0.180. Be careful here. Is this the right value? Look, this is what's in the question, right? It's not E naught. This is E. That's really important. That's the only thing you need to be careful of here. See, look at this. V, or the voltage, or this is same as E, is equal to, of the cell is equal to 0.180 volts. So the maximum work over here will be whatever this cell is saying, which is this over here. So it's minus 6 into this, which is, 1.08 F. So this is a negative value, but the work that you get out of it, the maximum work, would be the positive out of it, which is 1.08 F. So this one's correct for sure. So here are the 4 things we looked at, and you can look at the correct options on your screen. But just need to do this diligently. Small places where you could mess up because of the number of things you need to keep in mind. So write everything down, do this slowly. I know this took a little bit of time, but it's important that we spend time on it. Some basic ideas tested, which were, what is the maximum work that can be taken out of an electrolytic cell? And this is where the Gibbs free energy idea comes in, right? Gibbs free energy means maximum useful work. When I was in school, I never understood the idea of what on earth you mean by maximum useful work. This is what it means. Yeah, the electrochemical output or something like this. Yeah. There are other forms of work as well that could be taken out, but since we're doing electrochemistry, let's look at this Let's look at this separately. So W max is now simply going to be equal to minus NFE, and the work extracted is going to be positive, so it's 1.08 F. So this one's correct. And the other options, you can see which ones match that are on your screen right now. This question will test our understanding of Faraday's laws. It's an integer answer that's expected of you. You have 3 cells connected in series, and some amount of chromium is deposited, chromium 3 plus is deposited. Using that idea, we need to figure out the 2 other substances, some information about the 2 other substances. So let's see. So we given cells in series, the masses of chromium and X that are deposited, these 2 values are given to us. We need to find the valency of X, the second element, and also the number of valence electrons in Y, the third substance that gets deposited. So what's the approach going to be like? Let's see. This is just an application of Faraday's laws. Series means the current is same. This is the single most important idea. That without this, you may not have an idea of what to do with this. Okay, so same current passes is the first thing you need to know. After that, it's just Faraday's laws applied in different forms. So number of equivalents that react are going to be the same throughout. You can use that and find the value n, the xn plus. And using the same idea, using number of equivalents of chromium that reacted, you can then get the mass of Y that deposited, and then get the identity, because mass would, from here you could get the molar mass. Once you have the molar mass, you have the identity of the substance, and then you can get the electronic configuration of Y. And then the valence electrons, that's what's required. Let's start this one step at a time. So repetition. The same current flows through all the 3 circuits, all the 3 cells which are in series, and the same equivalents are deposited. So the equivalents of chromium are simply going to be given by this expression here. 1.3 grams, that was the mass that was deposited, divided by the mass of chromium into the number of electrons per mole that were transferred. Now this value is simply 3 electrons per mole, right? Because what happens is that, just bracket. Let me make that properly. So what happens is CR3 becomes CR. Or, you can also write this as 3R3 plus. It's the same thing. So 3R3 plus becomes CR. That's what's happening. So there's a 3 electron transfer. And from this, the mass of chromium is given to us. The value is 52 gram per mole. Okay. So let's do that calculation. You get 1.3 divided by units. Units are important. 52 gram per mole times 3 electron per mole. This gives you, what does this give you? This gives you the number of equivalents that were deposited, right? So number of equivalents simply going to be, divide this. This is 1 by 40. So this is 3 by 40, which is 0.075 equivalents. Okay, that's it. Now from this, we're going to find out the number of electrons, the xn plus, that n value, and also what to do with Y, and finally get the identity as well as the number of valence shell electrons in Y. First thing, equivalents of Y are going to be equal to equivalents of CR, and also the equivalents of X, right? So in this case, what is the mass that gets deposited? It's 7.5 grams that got deposited, and this is X, not Y here. So this is X over here. Let me erase that and make that properly. This is the equivalence of X we're talking about. It's going to be equal to the equivalence of chromium. So the mass I got deposited was 7.5 grams. The molar mass is given here to be 200 grams per mole. So that's what I've just given you the equation on top, right? I'm just substituting the same thing here. The deposited mass, this is the deposited mass, divided by the molar mass times the number of equivalents per mole. So the number of equivalents per mole here is going to be n. I'm assuming that xn plus becomes x, right? That's a fair assumption. And here, this is the expression that will tell us what to do. And you already have this value to be 0.075, right? So just substitute that there and you get n. So one variable, one equation. So when we split this entire thing into 3 different parts, each having one variable per one equation, the same equation, it's a very, very simple thing to do. That's what we're doing. So the number of the n value simply is going to be, I'm just taking this to the other side. So you get 200 into 0.075 divided by 7.5. So I think this is a neat and nice number. What you get here is 2. Everything else cancels out. Does that make sense? Yes, it does. So 7.5, this is like dividing 7.5 by 100. And you get this n value to be 2. So that's it. And if the n value is 2, so a part of my answer, I need to add this, right? this N plus the valence shell. So I'm halfway there. Valence shell electrons of Y, right? Electrons of Y. So this part is 2. We've got that. Let's look at the next one. What are the valence shell electrons of Y? This one's Y. So equivalence of Y is going to be equal to the equivalence of chromium. The mass deposited here was 2.38 grams. I'm using the same equation again. This again is Y gram per mole is going to be the mass, whatever that is. I don't know what that is. Once I get this, I'm going to be able to figure out the identity. Yeah, that's the goal. So equivalence of chromium, again, this is 0.075 and Y gram per, so let me bring this to this side. So now Y is going to be equal to, and take that side. So I get 2.38 into 2 divided by 0.075. So this gives me a value of approximately 63.5 gram per mole, and this is copper. That's it. Once you know that identity, you can find out what the valence shell electron is going to be like, right? I think from here on, it's pretty doable. Let's see. So copper has a electronic state of argon. That's the noble gas, the closest noble gas. 4s1, 3d10. Now, here, please don't write the valence electrons to be 10 because that's not correct. The valence electrons are 1. The 4s is outermost shell, yeah? So this is the other half of the picture that I'm looking at. And please don't write 10 because this is the energy level, right? This is the way things get filled. If you remember, even when you're doing other things with these sort of configurations, the first electron to go out is always the outermost electron, which is from the 4s or 5s or whatever. The s electron, the d electrons come later. Yeah. So this could be another way for you to remember. This is a simple idea, but students sometimes make an error in this. Okay, so I've got 2 from the other one, 1 from here, and the answer that I have is 2 plus 1, which is 3. There you go. So quick recap, although I did a lot of that during the numerical. What we do here is we use the basics of Faraday's laws. Yeah, the approach sums it up very nicely. We started with how do you get the number of equivalents of chromium. Use that to figure out the number of electrons of X, and then same equation is used to figure out the atomic mass of the element Y. And then using that, figure out which element it is, figure out the electronic configuration. From there, be careful about the last part. You get the atom to be copper. So it's argon, 4s1, 310. The valence shell is 4s, 1 electron, right? So 1 from here and 2 from there, the X value, and the total answer was 3. Here's a paragraph set of questions. We'll look at the first question first. Let me give you what's the data that's in front of you right now. There's some sort of molar concentration of a salt, NaCl, and molar conductance is given to you with respect to those concentrations. And then there's some other data about if you have a specific concentration of the NaCl solution, then the resistance value is given, and infinite dilution conductances, Cl minus and SO4 2 minus values are also given. Now, what we have to do in the first question is find out the molar conductance of NaCl at infinite dilution. So what's given to us? Well, we just have the concentration and conductance values of NaCl. We just need that table. You have to solve this one. And we should be able to figure out lambda infinity m or lambda naught m. So let's see what we need to do. What's the approach going to be like? Well, use this expression. This is for strong electrolytes, right? If you have a strong electrolyte, then this expression gives you the value of, gives you how lambda m is related to lambda infinity, and it's dependent on concentration. Yeah. So, and the things that you don't know here are this guy here and this guy here, B and lambda infinity. So if we form 2 equations and we have 2 variables, we should be able to figure this out. These are the 2 variables. How do you get 2 equations? Use the data points. We have 3 data points, right? You can use 2 of them and then get C. We can plot in values of C and lambda m and get lambda naught m and B. So 2 variables, 2 equations, solved. That's it. Just that for this first question. But this is really important because the results of this will be useful in the next. You cannot do the second and third question without this one. So, okay. So when C is equal to 4 into 10 power minus 4 molar, lambda m is this value. So using the expression, let me write that again. Lambda m is equal to lambda infinity, or lambda naught is the same thing, lambda naught m minus B times root C, right? So according to this expression, 107 is going to be equal to whatever this constant value is minus this other constant times root of 4 into 10 power minus 4. Okay, if I just simplify that, that's going to be equal to 107 equals lambda infinity m minus B times 2 into 10 power minus 2, right? Just a simple square root taken over here. That's my first equation. Let me mark that as equation 1. So what I have here is simply the same thing, doing the exact same thing again. I'm going to form a second equation, and this on the left hand side I have 97. This lambda m value that's going to be equal to, again, constants I don't know, which I'm going to just put here, and root of 9 into 10 power minus 4. Luckily, these are you can work with them pretty easily. This gives me lambda infinity m minus b times 3 into 10 power minus 2. So I have two equations, two variables. I just subtract them both and I can get the b value, right? So let's do that. If I just subtract, which is larger, this one seems to be larger, right? So I'm going to just subtract them both, and see, 1 minus 2, right? When I do that, if I do that, I get 10 is equal to b into 10 power minus 2, which gives b to be equal to 1000, pretty large number. So b is 1000. Okay, we've got that. Now from this, you can get the lambda naught m value, right? How's that? Just substitute in this first equation. So lambda naught or lambda infinity m is going to be equal to 107 plus b I'm just substituting that as 1000 directly. So this is b times 2 into 10 power minus 2, right? So when I do that, I get, what do I get here? I get this to be 2 into 10 power minus 2 is just, taking these two zeros out, this goes away, 20. So this is 127. So I get lambda infinity, lambda infinity m molar at infinite dilution to be 127. What are the units? The same as what was in the question. Yeah, so that's going to be ohm inverse or mho. It's the same thing. Yeah, I like writing mho. I just like doing this. I'm going to do that. It's the same thing. Yeah, ohm inverse is the same as mho. Okay, this is this per mole. This is the unit that I have, and that's it. This is the answer, and that's what option is that? I think that's option C, right? So that's the answer, right? Here, this is your answer. So as a quick summary, again, two equations, two variables. Just use the formula that you know for strong electrolytes. Yeah, how lambda m is dependent on the infinite dilution value of lambda, which is lambda naught m, and also on root of concentration. There's a concentration. There's a constant term b also that is there before the root c value. You can use the constant be b or a or whatever other value. I chose it to be b. Some other places, some other books have it as a. So yeah, there you go. That's the answer. 127 ohm inverse cm square per mole or mho cm square per mole. Okay, so this is the second question from the whole paragraph. It's linked, yeah? We need to find the cell constant for this entire setup that's given to us. So, a lot of data given. Which one do we need? What data do we need specifically to get started? Well, we need to use this, yeah? We need to use the concentration given as 25 and 10 power minus 4 molar, and the resistance value is 1000 ohms. I'll tell you why in a bit. Because we need to find cell constant. Now, how are they related? What's the approach we can take here? You see, we know the value of lambda infinity and b. Yeah, I think it was something like 127 and this was 1000. I'm not writing the units right now, but these were the numerical values. And from this expression, this is from the previous question. Okay, this is from the previous question. We know these values. So we can find out the lambda m at this concentration. Hold on to that thought. After we do that, we can use this basics of what is resistance, what is conductance. Use conductance. This is conductance. Yeah. G is conductance, TANCE. From there, you relate it to K, kappa, which is conductivity. Yeah, I'm slowing down here because this is important. And this is more of a revision of the theory of the whole ionic conductivity idea. All right. Now, this G star over here is simply, the cell constant, which is what we need to find. This is L by A, this expression, this quantity over here. So, we need to get conductivity from here. Once we get conductivity, we can substitute in this expression because we know R value. And if we know this, we can get this. How do we get conductivity? Well, the molar conductivity which we found here, this is simply the kappa value per mole. We'll figure out the units. Don't mug that there's something 1000 and all that. I'll tell you how we get that from the basics. Yeah? As much as possible, let's not mug too many equations. And this one is direct. Yeah? Molar conductivity is just a conductive value per mole. So we'll divide by concentration, figure out from basics. All right. Then there's a simple substitution, get G star, which is the cell constant and the required answer. So let's get started one step at a time as usual. This expression lambda m is equal to lambda infinity, lambda naught m minus b root c, right? Now what were the values over here? Lambda m is what I need to find out, right? And this is going to be, yeah, this was I think 127, right? 127 minus 1000 times root c. Root c here is simply root of 25 into 10 power minus 4. So this is just the same as a 5 into 10 power minus 2, right? So that's it. So lambda m will now be equal to 127 minus 50, right? Yeah, this basically cancels two zeros. So there you go. This is 77, units are important, mho or Siemens, which is the same thing, centimeter square per mole. This is the value at that concentration, at this concentration specifically. Once we have this, we use the basics of physics, right? Rho R is equal to rho L by A, G is 1 by R, which is conductance, and K times kappa times G star. This is what we eventually need to find. So that's why we're finding kappa, yeah? This will help us get to this. This is conductivity as usual. I'm doing this a little slowly because just doing these three numericals will give you an entire summary of all the theory that you need for conductivity of solutions, yeah, electrolytic conductivity. So lambda m is kappa by concentration. What is the concentration? Concentration here, yeah, again, 25 into 10 power minus 4, right? Molar, mole per liter. That's what you have over here. By kappa should be equal to, what is this lambda value we just got here? Oh, not 127. We just calculated this, right? This is simply 77 is what we got. Hold on, let me just work that out. Yeah, this is 77. Again, units, slowly. Centimeter square per mole. Now, this is where we kind of do a little bit of accounting. Yeah, 1 liter is equal to 1000 centimeter cube. This is where that number 1000 comes into it. Most students try and mug that. I would suggest that we don't need to do that. Yeah, we have units on our side. There's nothing that can stop us. We're good to go. So this into centimeter square per mole and into 25 into 10 power minus 4 mole per liter into 1000 centimeter cube per liter. Okay, so we cancel it out slow and steady. So what goes here? This 2 goes away, this 3 goes away, mole gets cancelled, and yeah, 77 into 25, whatever that value is. Scroll down, give me some more space. So this is 77 into 25. What are the units now? Per centimeter. That's it. Oh, mho per centimeter. I forgot mho, right? That's the most important guy here. That's what makes the conductor. I was wondering where did that go. So this is mho or Siemens per centimeter. Sounds about right? This is the right unit. But let me check. Did I make this right? I had mho centimeter square per mole. Okay. I cancelled out everything else, and this is the only thing that remains. So yeah, this is kappa that I have over here. Okay, now from here, let me use the kappa value and get G star. It's simply kappa times resistance, right? Kappa is 77 into 25, and resistance here is just 1000. Oh, hold on. I made a small goof up, right? There's 1000 in the denominator. So this should be 10 power minus 3. Okay, so this is let me erase this so that there's no confusion. Yeah, there's a 10 power minus 3 here. So this is 10 power minus 3, and then there's another over here. From here we get 10 power 3. Okay. Oh, and there's another 10 power minus 4. My bookkeeping is bad. Be careful. I hope you don't make this mistake. There's a 4 here and a 3 here. So this basically becomes 10 power minus 7. Okay, from here. So the kappa value is actually 10 power minus 7. Yeah. Okay, there you go. Now that looks nice. So I have this into 10 power 3. Why is this 10 power 3? 10 power 3 is just a resistance. Yeah, resistance of this setup was given to be 1000 ohms. That's what I'm using here. And this gives me the G star value. That's it. I plug this in. So this happens to be, yeah, so this goes away, this goes away. I have 10 power minus 4 remaining, right? 7 minus 3 is minus 4. 7725, big number, 1925. And when I remove the 4 decimal places is what I get. Units, did I, let's check the units. Okay. this here, the units of kappa were mho per centimeter. And okay, let's stop writing mho. It was all fun and games, but just to ohm inverse, yeah, so that I'm not messing with you guys anymore. And this here is just ohm, right? So there you go. These get cancelled out. So this is cm inverse. My units are fine. Okay, that's the answer. 0.1925 centimeter inverse, which is option D. Quick revision of everything we did. Well, we use the constant values, yeah, in lambda at infinite dilution as well as B from the previous question. Then we found out lambda at this given concentration. Once we had that lambda value, keep that there. We held that back. And then we found out conductivity. Yeah, using that conductivity is the same as, well, molar conductivity is the same as conductivity per mole, right? So I divided conductivity by concentration, rearranged things, got the value of kappa, conductivity. Then we used the basics of physics and all that, and got G star, which is the cell constant, is going to be equal to kappa times the resistance. And there you go. We made sure of the units, the exponents, all of that, accounted for everything. Left the numbers, calculations right in the end. Always do that. Do all the exponents and cancelling of units. Make sure everything is correct. And the actual calculation can happen right in the end, which is 0.1925 centimeter inverse, which is answer option D. Here's the last question of the paragraph. Everything changes here. You have a different electrolyte altogether, yeah, Na2SO4, and the concentration is given to us to be C dash, is what I've written out to be. It's 5 × 10 power minus 3 normal. And the resistance also changes, yeah, R dash becomes 400 ohms. We need to find out lambda M for Na2SO4. That's what's been asked of us here. So what gives? How do we start this sort of a question? Remember, we need to use everything we've done so far in question 1 and 2. That's what would help us. And what we did there is we found out G star is the same cell. So if the cell is the same, the cell constant is the same. So all those stuff is changed. Conductance changes, resistance changes. So hence K dash also changes. And if K dash changes, lambda dash changes. So yeah, that's it. We know G star, right? Using this, we get the value of K star first from this equation. K dash, and from here we go in and calculate lambda dash, which would give us the value that you want. Remember, this is just kappa dash divided by concentration. Yeah, don't worry about the 1000 thing calculation, all that. We'll do it by units. Okay. So K dash is G star by R. This G star, I remember, was something like 0.1925 centimeter inverse, right? And the resistance now is 400 ohm. So let's take care of the units. I always write it down in this manner. So you have this. And let's now then find out lambda dash M, which is K dash divided by concentration. One thing you need to be careful about is that the normality is given to you, not the molarity. We need to do things in terms of molarity. For the sake of convenience, we can also use lambda equivalent, but that's not what's been asked for. You can do this in one of two ways, but they all arrive at the same conclusion. So we'll do it in this manner. You know that normality is molarity times n. Remember, n comes after m in the alphabet, right? So n is larger. That's how I remember it. So m into n should give you normality. So now molarity would be equal to whatever value you have, the normality divided by the n factor, which in this case is 2, right? That's what I've given that over here. So this is the concentration that we have over here. Now we need to do this calculation, right? This calculation here. Let me make some space. Scroll down a little bit. Okay, so you have lambda m dash is equal to K dash by concentration. So let's do that. I have kappa to be 0.1925. That was a bad 5. Let me make that properly. It's 1925 centimeter inverse ohm inverse, right? Yeah. Divided by 400, right? That's what I had over here. Just checking that. Okay. So that was that. And then what I need to do is multiply this with divided by the concentration, right? Here it's into 5 by 2 into 10 power minus 3 mole per liter. Now I'm doing the same thing I've done in the previous question. Yeah, I'm just getting rid of the liters. I don't need that. I need stuff in centimeters, right? Because that's the unit I have over here. If I cancel this out, this comes here, this goes here, so it just becomes centimeter square. And this, yeah, so, and if I write this on top, this becomes mole inverse. So this entire thing here, this is basically the unit of this thing here. This is the unit of lambda m. So this is just a way to check if what I'm doing is right or not. Yeah, if I've accounted for everything. And now this looks really messy, but all I need to do now is just, well, get into it and, get some numbers here. So yeah, I can write this as what happens here. Oh, cool. I think stuff gets cancelled out nicely. Just 2 here becomes 2 here. So this is 200, 500, 200 is 1000. So this and this cancel out. This is 1000 and this 10 power 3 and this becomes 10 power minus 3, which I have cancelled both of them out. You have another 10 power minus 3 in the denominator. So I think this goes on top. So yeah, you basically get, you get 10 power 3 into 0.1925, which is simply 192.5. Oh, that was easy. This is why I keep saying, always do substitutions in the end. Yeah, look at this. Everything cancelled out nicely and neatly, and all you had remaining was this. Don't forget the units, although the question is not testing that. We like taking care of units because they always take care of us, like we saw in this case. And this is the answer, 192.5 ohm inverse centimeter square per mole. Now, a quick recap. We just used the idea that, okay, although we changed everything, we changed the entire system, we got new resistance, but there was the same cell. So the G star value, the cell constant was the same. We used that to get the new conductivity and hence the new molar conductivity. Be careful, in this question, normality was given. We converted to molarity and then did it. Or you could have done this entire expression, got the value of lambda equivalent and then got lambda m. That's also the other way to do it, but you get the same answer anyway. There you go. That's the answer, 192.5 ohm inverse centimeter square. Oh, per mole. Yeah, there you go. Count of units. That's the answer. Another question that expects a numerical answer from you. Very short question. You have 2 weak acids. pKa1 is given to you to be 4. pKa2 is given to be 5. A cell is formed with a salt bridge and all that. And this is at STP. Find the EMF. Short and sweet. Let's see. The approach here is going to be that, look, there's a concentration cell that gets formed. So the lower pK is a stronger acid and that becomes the cathode. And that's why I set it up like this. You see over here, this had a value of 4, this had a value of 5. I'm talking about the pKa values, right? So that becomes a cathode because of the concentration cell. Only then you get a positive EMF from the cell, which is the goal. So yeah, from here on you get E anode, E cathode, get E cell, and this is the Nernst equation that you would use to get there. Only thing you need to be careful about is what is the H plus ion concentration, because that would go into this Q value. So let's get started. The repetition, yeah, this concentration cell, cathode concentration is greater than anode concentration for positive EMF value. And both the reactions are the same, which is this over here. E naught is going to be 0, concentration cell, yeah, again. So Q is equal to this expression over here, just this. E is E naught minus RT by NF ln Q. Now, if I convert this to log and I, use the usual approximations, I get this to be simply E naught. Yeah, I get E naught minus 0.059 into log Q, right? This is a standard approximation that we use a lot, just substituting values. This is at STP and, counting for 2.303 and all that when you convert from ln to log. Now, this over here, if I take a log of this on both sides, yeah, then all I get here directly is E would be equal to minus 0.059 EH. That's it. Now, all we need to do here is find out pH. What is pH? Well, using this standard dissociation constant idea, you get this. And so a good approximation, because K is simply C alpha square by 1 minus alpha, which is almost going to be equal to C alpha square by 1, because alpha is really small. You have the pK values, right? So this is C alpha, this is C into 1 minus alpha. I'm quickly going over stuff like assuming that you've set up the equilibrium, and this is what you get. So C alpha is the H plus ion concentration, okay? So H plus ion concentration is, I'm just writing that down here. If this is equal to C alpha, then your pH value is simply negative log of this, right? So I take negative log on this side, on both sides basically. And because from here I get that alpha is equal to under root K by C. This is a good approximation that I can take. So if I take negative log of both sides, I get pH is equal to half pKa minus half log of C. Now, since the concentrations are both the same, that's also given to us in the question, this factor kind of will go away. Why? Because I'm subtracting two values, right? So let's do that. Let's go ahead and see. So E cathode is minus 0.059 pH2. E anode is minus 0.059 pH1, whatever these values may be. Let's see. Wait, is this correct? Hold on. Which was the cathode? Which was the anode? Cathode was 1, anode was 2. Okay, yeah, let me correct that quickly. This is going to be pH1, this is pH2, right? This is pH2, this is pH1. And once I do that, what do I do? Yeah, so E cell is simply going to be pKa, this is a half outside, right? pKa of 1 minus pKa of 2, right? That's all I have to do here. Yeah, I'm just subtracting both of these. What did I do this? Yeah, E cell is E cathode minus E anode. That's the result that I use. So a little bit of bookkeeping here. Just be careful with the signs and all of that. A lot of places where you could mess things up just because of the signs that we've used. So this gives me the value. I just depend on the pK value. Now this is 5, weaker acid, the anode, minus 4. Yeah, that's it. Oh, times 0.059, right? Because remember, there was that value also there. pH was this is fine, but E was this value also. It also had 0.059 outside it. So which is also written here. So the answer is half of 0.059, which is 0.0295. That's the answer right there. So a really cool question. The only thing you needed to do is realize where's the cathode, where's the anode. If you mess it up, you'll get a negative answer, and luckily, well, the integers don't expect negative answer right now. But the other thing that you need to be careful about is how to get H plus ion concentration. Set up a basic equilibrium idea, get H plus ion concentration, figure out how E depends on pH, right? From that idea. And then after that, it was just a simple thing of E cell is E cathode minus E anode. Substitute that. We got the value to be 0.0295 volts, right? That's unit. So we put that there. That's unit. But the number is 0.0295.
For more videos and live lectures on the JEE, click on the subscribe button now.